Before moving to the discussions on optimizations, I would like to complete the discussion on genetic algorithm that was initiated in the last class. That hardware software partitioning problem is also a variant of an optimization and can be solved using genetic algorithm also. I will quickly give an example without going into all the details, because it is expected that you know about the genetic algorithms separately. Okay. So, here we start with say a task graph, as can be seen here. Okay. Tasks A, B, C, D, and here are the dependencies A, you can see, and there is a time constraint that has been specified, which is specified in this way. The time constant from A to D. A to D is 5, some 5 units of time. All right. I could have specified from A to C, C to D also, but that is not specified here. Also, so these are the functions, and for each of these functions A, B, C, D, let us assume that we have got implementations like U A implementation is, I am just showing some integers 2, 4, 5, 6. What does it mean? 2, 4 or 5 or 6 can implement A, this function A. Similarly, U B is 1, 3, 7. This is a toy problem, absolutely toy problem that I am showing you. C is 4, 5, 6, 8, and D is most flexible, can be done by 1, 2, 3, 5, 7, 8. So, for each of them, these are the candidates. Okay. Now, suppose I take a chromosome, say I take a chromosome 101, 110, 001, 010. Okay. As a solution of for A, solution for B, solution for C, and solution for D. Right. Now, so for each solution in this chromosome, I have taken the code length, the length to be 3. That means, each solution for each task A, B or C or D is given by a gene of length 3. Therefore, my total chromosome for 4 tasks is of length 12. All right. So, now suppose that means, now this one is a solution. This solution may be, say, if I say that 101 is actually, I can write it in this way, the implementation of A is 101, and suppose that is 4. It is not a binary, 101 is not the binary of 4. 101 is the code for device 4, because it could be implemented with 4, right. Okay. So, similarly, say if B implementation, B's implementation is what is there, 110, 110, and suppose 110 is 1, because for B, 1 was one of the possibilities of implementation. Okay. Similarly, if C implementation is 0 0 1, which will be 5, and if D implementation will be 0 1 0 0 1 0, and that is 3. So, 4 1 5 3, I can see that for 1 4 was a candidate, for this one 1 was a candidate, 5 was a candidate, and 3 was a candidate. So, there is one possible solution. This chromosome is depicting one possible solution. In that way, for all the possible solutions, if I have a cross product of all these, so I can have 2 1 6 2, all those things could be possible solutions. Now, each of these solutions, one chromosome depicts a solution, and for all of them I carry out a fitness function. For each of these chromosomes, I will compute a fitness function. So, and the fitness function that can quickly be decided on, say, I say fitness function f is fit is, say, the maximum of the cost penalties in a population, the maximum penalty that I can pay. So, with all these we will have a population of possible choices, right. If I take the cross product of all these, I will have a huge set of chromosomes, right, and that is all possible solutions together, and the worst maximum cost I take as fit, and for every solution I take a find its cost penalty. So, I can compute a fitness as how much the cost penalty reduces, how much this fit reduces. So, there is a cost penalty. So, there will be a value for this, and I normalize with this. If the time penalty is false, time penalty is false means what? Two functional elements cannot be scheduled at the same time, and that has been done already, say in a solution that has been done. So, that is false. Okay. Now, similarly, I mean, and another thing is that if the time penalty is valid, say for example, I have got a time constraint here. So, if because of this allocation I violate this, then the time penalty is violated. Okay, then time penalty is true. And also if concurrency penalty is false. Okay, that is one. Concurrency penalty means if any two functional elements are concurrent in nature and both have been assigned, say for example, software implementations, then the concurrency penalty is coming in, right. If in a particular solution they are concurrent, but I have put both of them into software, then there is a concurrency penalty. So, if none of them are the case, I compute the fitness here. Otherwise, I can say, let me fit minus cost penalty divided by fit multiplied by time penalty. I can put a time penalty weight, some time penalty weight. So, if time penalty is true, okay, and concurrency penalty is false, then this will be my fitness function. Similarly, if concurrency penalty is true and time penalty is false, then it will be multiplied by concurrency penalty. If both of them are true, then it would be fit times time penalty weight into concurrency penalty weight. Accordingly, if there are both penalties, my fitness is reducing. So, accordingly, I will have different fitness functions for the different solutions. Next step, what is done in a genetic algorithm is I do the crossover. Typically, in genetic algorithm, if I have two chromosomes and I can select probabilistically any crossover point. All right. If I do this crossover point, then I take this part of this and this part of this to come to a new chromosome. So, a new chromosome will be something like this, right. That is what crossover gives me. There is a crossover between these two, is it giving me new one. And in that way, by doing the crossover, I will get new solutions. But in this case, I cannot probabilistically do anywhere. What do I have to do? I have to do it at the code length points. I cannot break a gene here, right, because this is solution for one functional element. For one functional element, I cannot have mixed solution, right. So, that is one restriction, and based on that I go on iterating on and ultimately I will find that the fitness function is increasing, and whenever any of the solutions have got their fitness below a threshold which is experimentally found out, that is discarded. Okay. Now, for all these, so for hardware software partitioning, we have discussed two particular approaches, I mean multiple approaches of course. One is absolutely hardware moving to software gradually, software moving to hardware, or a consistent leveling problem, or the the genetic algorithm. Either of these, the greedy of course do not guarantee the optimal solution. Okay. The consistent leveling problem, if we try to solve using some domain specific heuristics, then also it will give us a local minima. And in genetic algorithm also we cannot always say that is a local minima, but whenever we come to a particular solution, we give a mutation, and by giving the mutation, that means one particular gene I change, and by doing that I again move away from the local minima. So, the experimentally what we find is the typical solution. Here is a solution of running the consistent leveling problem, hardware software partitioning version of the consistent leveling problem. You can see here on the y axis is the cost and the x axis is the number of nodes expanded during the search. As we go on expanding the nodes, ultimately we come to it goes on decreasing, and we find that after 125k nodes expansion, we have come to a point after which we are not economizing any further. Now, you may not like to devote so much time for the hardware software partitioning computation, but the beauty of this sort of branch and bound is that if the more time you specify, the better solution you will get. So, you can come anywhere here and find a good enough solution, because ultimately we need the good enough solution, right, satisfying solution. The same thing happens for genetic algorithms also. We get a average cost, actually the curve comes like this. Sorry. The average cost is coming down something like this sort of nature, and with mutation the given here, we can find that here is the generations. number of generations, and here is the cost. All right, we get similar curve. Okay. And if we look at the best cost that we are getting, the best cost comes to something like this, and then remains a while here and then comes down like this. All right. So, it is gradually coming to a better solution. So, either of these, depending on your requirement, you can formulate when you actually delve in doing a hardware software partitioning for a real life situation. Given that discussion on hardware software partitioning, which of course takes into account, now all these discussions was based on the availability of a good library which had the different costs mentioned. Typically or ideally, it should also have the power cost of the hardware devices that are there should be mentioned. But in our experiments or the discussions that we have done, we have talked about the area cost, and all those power cost can also come in. Right now, we will be discussing on some optimizations that needs to be, that can be carried out at the compiler level. Till now, we have talked about the architecture level, hardware software partitioning and everything. Now, at the compiler level, we can do number of optimizations, and we will briefly discuss those. For example, one thing that we can do, we can merge the tasks. For example, here I have got a task graph. All right, you can see there's T3 and T4. I can merge these to be T3 star. What is the advantage? Advantage is, if you think of the overall computation time, whenever a task ends, another task starts, then there is a context switching overhead from the operating system. So, that context switching overhead will be reduced wherever I can merge the tasks. We can show that we can have more global optimization in the machine code and reduced overhead of inter-process communication. For example, and also we can do, just like as we can merge tasks, we can split tasks also. Say here again the same graph, but suppose this task T2 needs a particular data. Now, till that data comes, T2 is held up, but it is probably possible to break up this T2 into these two parts, where this part is not requiring that data, and I can go ahead and accept the data here. So, the amount of blocking on resources is reduced. Okay. So, that gives us more flexibility in scheduling and possibly improved result. Okay. So, here is an example, and this can be done automatically. So, you see here there are two processes, one is get data and other is filter. Now, this get data is taking the data from input in, and the filter has got two data inputs, one is a coefficient and there is the data that is being sent by the get data, and filter is sending out the out. Now, what it does? It comes here, reads a data and through the in and computes the sum and sends the data to the sum, and after a while it sends the average through this data port, right. Now, what is this doing? This one is selecting either data or coefficient. This you must have heard about the programming language ADA. Okay, it is a ADA-like construct actually, and this is also ADA-like construct implemented in a programming language called FlowC. Now, here select means nothing, that it is looking at these two input points, and whichever gets the data, it will start on that, right. So, if the data arrives, what it does? It reads the data and ignores. If n, it waits for n and actually waits for the average. After this n, this average will come, right. Here it is going on sending data, ultimately after n data it is sending the average. So, it is actually interested in the average and then it writes that out. If the coefficient comes, then it reads the coefficient, all right. So, that is, now you see there are 3 reads here, one is here, one is here, one is here. Now, each of them can be blocking. Instead, see the tasks, they have already started, all these have already started, but it may be blocked on any one of those because the data is not available, right. Therefore, it is possible to break this out, this particular task. You understand that it is reading this, suppose this reading is not done, then this is also not coming, all those things are happening. So, if I can break it down as was done by Cortadella, a researcher who put this example in, there is an initialization task, there is a coefficient computation task which is separately reading the coefficient, not integrated with this task. So, the non arrival of coefficient will not block it, block this part here, this entire process is not blocked. So, here you see, and this one is reading only at the beginning. So, nowhere I need to wait further. So, it is reading the sample. So, I rewrite the code simply. So, just to show that by rewriting the code, I can have that task breaking, and this j equal to n is never true, and j here this part will never be true and this part will always be true. You just look at this, this part will always be true, right, because data is coming after here, after n samples have been read. Here the n sample, this is when the first data has been read. So, that will never be true, this one will be true. Therefore, I need not bother about this. So, look at the scenario as it was here, where I had put this. Now, when I split it, I have put it, merged these two together and rewrote the code. I have merged these two and rewrote the code as coming in here, where this j equal to n is not actually required here, right. So, it can be very well optimized to be, this was never true, the entire code can be optimized in this way. And present day compilers can actually do that, and by that we are saving on a number of things. We are saving on the size of the code, saving on the number of input outputs, all those, right. Another very important and very useful optimization besides task splitting, task merging and rewriting the code is loop transformation. Now, you know that Fortran and loop is a very common occurrence in DSP programs and most of the many of the embedded system applications. You know column measure and row measure, right. So, in Fortran an array is stored in a column measure form. That means, it may be a 2-dimensional matrix, but ultimately it is stored in a linear array. So, in a linear array, the k 0 then k 1. So, for the first column, corresponding to the first column, all the rows are stored, then second column all the rows are stored, third column all the rows are stored. That is how it is done in Fortran, but in C it is row measure. So, first I stored the first row, then the second row, then the third row, that is a row measure order. So, that we have to take into account when we do optimization. Now, suppose I am trying to deal with an array p j k, all right, p j k is an array. Now, you see there are two loops. One is k 0 to m, k 0 to m means I am moving column wise, other is j 0 to n row wise. So, first I move column wise, and then move row wise. Inner loop is in row wise form. Which one will result in what? Since C compiler will store it in a row measure form, if I do this, this is a row measure form, right. So, every time for as j is changing here, I have to go to this, then this, then this, then this, again come back here, here, here. But what is actually done in my cache memory? The contiguous blocks are taken, therefore, there will be cache misses all through. So, that leads to poor cache behavior, and poor cache behavior means what? More time and more number of cycles wasted, and each of the cycles lead to switching, and each of the switching consumes power, right. But if I had done it in this way, the same thing I could have done in this way, right, then I would have obtained good cache behavior. You see, so I can do the loop transformation in this way. Best performance for innermost loop is this. So, it gives me poor cache behavior, this gives good cache behavior. It is obviously memory architecture dependent optimization. So, what can be done here? You did not look at the entire code, but what has been done here is a compute ijk for outer loop I, middle loop j, then k, and ijk is being added to ijk, all right. Some funny things being done here, but if I go on doing it in a loop, then and if I do it in this way ikj, in that case my timing, the number of the total time will also be reduced because of the cache miss will be avoided. Therefore, by such loop transformation I can save, and this can be done at the compiler level. So, here is a typical example. You can see it is very much architecture dependent also, how it stores and all those. You can see that the loop structure ijk, if you do this one, all right, this one the improvement will vary, ijk, ikj, jik, jki, you can see jik is giving best here, and in this case also jik is giving best among Sun Spark and Intel Pentium. So, that is some result that you can get. Now, another thing is loop merging. Let us look at this for j to n j plus plus, okay, and pj something, and then j to n pj sum equal to pj plus something. Now, if the loops are small enough, you see there is a loop overhead. What do you mean by loop overhead? Loop overhead means that when a loop is being executed. So, the linear part is computed, and then you go back and see whether the loop, you have to do the incrementation, and we have to see if the loop termination condition has been met. And this is a continuous overhead that you will have to incur all the time you are doing this. If a priori we could compute how many times the loop will go on, then we could have done by instruction, machine level instruction, that loop I could have done something like repeat n times. So, automatically I know a priori it will do n times, just as for loop I know it will do n times, okay, or n by 2 times, whatever. That is one way. The other way is that you can also, for the loop overhead, we can have some hardware, like if you recall in DSPs, we have done automatic address generation and index update. So, if there be some such hardware, then that can also be used. Now, if the loops be small enough, then if we adopt zero overhead loops, these two things that we mentioned are also known as zero overhead for looping, then it is fine. Otherwise, we will get better locality if I do this. If I merge these two loops j 0 to n, we can find that the loop size is same, right, loop number of iterations is same. I could have clubbed them, and by clubbing them not only I have better locality, but also I can do parallel execution. In this loop I do these two things together and again go up. So, my objective is to show you some of the techniques, there are many and people are working on many such, by which we can optimize on the code. So, here you see simple loop. First, let us say SS1. For I equals 0 to size j, ij is ij plus 17. For I equal to 0 to size, j equal to 0 to size, bij is bij minus 13. I do it explicitly. Okay. Here, what I do is the same thing. For I equal to, I just take I equal to 0 to this thing, and inner loop I merge. What has been done? What is the difference between these two? Here, the j part has been merged, the one I, and the j part I do for A, I do for B. Keeping the row fixed, I do for A and I do for B. All right. I should save time in that. And here, I even merge these two. Why do I keep them? The range is same. So, I can further merge these two. So, I come to this and one j do both and then move j, right. Comparatively, what is the performance you see? Except for some architectural peculiarity of Spark, leave aside this one, look at these three. SS1 compared to that MM1 is better. If as I merged, I could get substantial improvement in 86, x86 and Spark. Okay. That is what we can gain by intelligently generating the code. Another technique is loop unrolling. This is a very common thing in compiler optimization and code generation as well as in embedded systems. Here, I can say for example, here j to n, j is 0 to n, I am doing something in this loop. I can very well do pj, pj plus 1, pj plus 2, all those things could be done together, because I know that I am explicitly unrolling the loop. Now, and here is it varies, I mean, what is the factor by which, how many you unroll. So, you can do pj and pj plus 1, then you go on doing the loop. Now, what will be the loop index incrementation will change. So, first in one loop I was doing only one update here, and I was doing n number of looping. Here what I do? I do 2 operations in a loop and do n by 2 looping. Thereby also I reduce, this is loop unrolling up to a level of 2, factor of 2. It can be also flattened wherever possible. Okay. But that will, if you flatten, then what will the problem? The code size will increase, right. Code size will be increased, and as the code size increased, your memory requirement also increases. So, all those things have to be looked into. Here is another technique that you can think of, energy aware compilation. So, if I optimize for low energy, what would you do in order to if you want to reduce energy? I want to reduce energy being the power integral time. I would like to reduce the time as well as the power spent. Okay. So, I will also try to reduce the missed memory cycles or even the memory accesses. If I can confine my computation within the registers mostly, then I save time, right. So, here you see a particular source code has been divided into 2 parts. One is, this one is mostly in the registers, this one. The computations are having minimal memory references, all right, only 1 or 2 memory references. Here I am having 3 or 4 memory references. So, as I go to the memory references, I am needing I needed less number of cycles, because the code size is less, but the power was more, energy was more. Here I have increased in the cycles, number of cycles, but I have reduced the particular the amount of energy. Now, this varies depending on, it will depend on how much scratchpad memory you have, how many you can do on the registers itself. All those things are not so straightforward. You have to do some sort of optimization for that. Here is another example. Say I 0 to 10, I am doing C is a I plus 1 multiplied by 2. Now, this one is being done in a loop. Here what I am doing, I am taking 1 a 0 in a register, and then 1 to 10, 0 is already taken. So, from 1 to 10 I am doing a register pipelining. I am just doing it in the register and not looking at the array any further, only just taking one element from the array, not 2. Here I had 2 accesses to the memory. Here I take in 1 and I go on, that one will be the earlier one. So, thereby I can do register pipelining and save on the number of loops. Also, there was the opportunity of doing this multiplication by 2 by simple shift and not multiplication. Thereby, I could have also optimized. Okay. So, energy aware compilation will require that there are different opportunities. One is energy aware scheduling. Okay. Now, what do I do in energy aware scheduling? I schedule the instructions, the ultimate result will not change. I will schedule the instructions so that the signal transitions are minimized. Think back of your computer organization or architecture courses. Whenever I am fetching an instruction from the memory, that is an opcode with number of bit patterns. So, if I schedule 2 instructions one after another, where there is minimal change in the bit pattern, that would minimize in the switching. Okay. Similarly, what sort of instructions I would select? These are related. Suppose addition and multiplication, I can do the same thing by repeated addition or multiplication or shift and multiplication. Now, I may also prefer not to do with shift, but do multiplication by 2 if I can save on the switching of the consecutive instructions. And the other thing that we have already shown is the exploitation of the memory hierarchy. Okay. That we have already shown that here also we are exploiting the memory hierarchy between the primary memory and the register scratchpad memory. In that way, there are different ways by which we can put in what are the elements we will put in the scratchpad memory. That is itself another issue, and for that again it can be modeled as an optimization problem. So, this discussion can go on, but my objective was simply to give you an idea that we can save on energy and we can optimize on the performance, not only by the hardware decisions that we have taken, but also at the compiler level. When we generate the code, we can look at different optimization steps and make a very efficient code, so that the overall system's energy requirement is minimized and the performance is met.